Hello everyone, and you're watching The Maths Geek. In today's video, we are going to be discussing a very interesting second order differential equation. So without any further ado, let's jump right into it. Alright, so here is our goal, our differential equation for today. Y double prime is equal to y, or d square y by dx square is equal to y. So basically we just want to solve for y, where y is a function of x such that the second derivative of y is just itself. And now today we are not going to be using the usual method, which is really you have a y double prime plus by prime plus c is equal to 0. And then you solve this, you convert this into the characteristic equation ar square plus br plus c is equal to 0. Then you have solutions depending on whether the discriminant is greater than 0, less than 0, or equal to 0. But today we're going to solve this using a very interesting method, which is by constructing the Taylor series, or rather the Maclaurin series of y, and solving this. So yeah, this is going to be much more interesting than the original, the classic method. So the initial conditions given to us are that f evaluated at 0 is 1 and the derivative of f evaluated at 0 is 3. So without any further ado, let's get started. So we first assume that y has an infinite Maclaurin series. So just an x to the n. Okay, and now we differentiate this twice. So we differentiate this twice. For that, we first differentiate it once and then differentiate it twice. So using the power rule and the product rule, that's just going to be this n times x to the n minus 1. And now again differentiating y prime, which will give us y double prime. We have this with us right here. And now, so we know that y double prime is equal to y. Now notice one thing, that we have x power n here and we have x power n minus 2 here. So wouldn't it be really good if I have x power n for y prime and y? So then I can get a recursive relation between an and solve. So first let's just note that the zero term of this. So if we put n is equal to 0, what are we going to get? 0 times something, that's just 0. So we can just really not consider the 0 term, remove it, and if we put 1, that's going to be n times n minus 1. So 1 minus 1 0, anything times 0 is 0. So we really don't need to consider any of the first two terms. So instead of starting my sum from 0, I can just directly start my sum from 2, as the first two terms are just 0. Okay, so now y double prime is going to be the sum as n goes from 2 to infinity of n times n minus 1 times an times x power n minus 2. Now here we have something good, but we have to now re-index this, right? Because that thing starts from 0, here it starts from 2. So I'm just going to replace n by n plus 2. So I'm just going to put n plus 2 is equal to 2. So the lower limit is n plus 2 is equal to 2, which gives me n is equal to 0. So that's good. So you can see why I have done this, just to re-index this, and now replacing n by n plus 2, right? So that gives us that we now have, really this is just the sum as n goes from 0 to infinity of, so n plus 2 times n plus 1, because we've just put n plus 2 in place of n. And now instead of an, we'll of course have an plus 2, and we have x power n. So now these two relations really look helpful, because we have x power n, and this is an infinite sum with the same lower and upper bound. So it's obvious that since two infinite sums with the same coefficient with the same power of x and the same lower and upper limits, if they have the same sum, then it must mean that we must have that an is equal to n plus 2 times n plus 1 times an, right? I'm just equating these, the general terms of these sums, because that's really when these sums are equal. So far what we've got is that an must equal to an plus 2, sorry, must equal to an times n plus 2 times n plus 1. And now we will move ahead. Okay, so this is our recurrence relation. Now what's important here are the initial conditions. F of 0 is equal to 1. Now remember that y was this infinite sum, right? So if we put f of 0, this really, as you can see, is just going to be a0, all right? And that's because it's just going to be a0 plus a1x plus a2x square and so on. So if you put x is equal to 0, all these terms are just going to vanish, and we just have a0 left, which is just 1, which is given to us. Okay, and now again, if we differentiate f prime of 0, so if we just differentiate this, now the first term is going to be 0 because, okay, n is 0 and we just have a1, right? So that's just going to be a1 plus a2 times x plus a3 times x square and so on. So again, if we put x is equal to 0, all of this will vanish and we're left with a1. So we know a0 is 1 and a1 is 3. So now these two facts will help us establish a recurrence relation between an for odd separately and an for even separately, because we have an and an plus 2. So n and n plus 2 have the same parity, right? That is to say that either both of them are even or both of them are odd. So from a0, can I write that substituting n is equal to 0 in our recurrence relation, I can write that a0 is 2 times 1 times a2. So a2 is just 1 half, all right. Now a2 is equal to 1 half. So can I put n is equal to 2 here to write that a2 is equal to 4 times 3 times a4. So therefore 1 half is equal to 12 times a4, which just gives us a4 is 1 over 24. And now you can try your hands on this and you get that a6 is 1 over 720. Now I really hope that you guys are able to see a pattern. If not, that's all right, because this pattern can really also be proved by induction. You can just recursively apply induction here to get that the 2nth term. Now notice for this, it is going to be 1 over 2 factorial, 4 factorial, and 1 over 6 factorial. Just know that n factorial is again just the product of all the natural numbers from 1 to n. That's if n is, of course, a natural number. There are other extensions too. So yeah, we have this, and we can actually prove that a to n is 1 over 2n factorial. So that's wonderful. We've got a, a general term for our for our even number coefficients. Now let's move on to the odd number coefficients. So let me write this over here. We know that a to n is 1 over 2n factorial. And if you're wondering, if you put n is equal to 0 here as well, you get 1 over 0 factorial. 0 factorial is 1, so that's just 1 over 1, which is just 1. Okay, so now a1 is 3. Again, using the recurrence relation, putting n is equal to 1, we get a1 is equal to 3 times 2 times a3. So 1 is 3 times 2 times a3. a3 is 1 over 6. Now again, if we put n is equal to 3 in our recurrence relation, we get a3 is 5 times 4 times a5. That means a5 is 1 over 120. Now I really hope you can see this resemblance here. If we put n is equal to 7 again, 5 again, we just get a7 is 1 over 5040. And again, you can notice that a2n minus 1, I'll just write a2n minus 1 for this, is actually equal to 1. Um, oh, 1 second, 1 second. It was a1 is 3, I'm sorry. So that's going to be 3 over 6. That's going to be 3 over 120. And that's going to be 3 over 5040. So that's just going to be 3 over 2n minus 1 factorial. Just in the same way as we had done this. So now we actually have our general odd term and our general even term. So from here, you just really have to it's just how you go about finding the sum.